Good afternoon, dear participants of the conference. I present a work, Neuro-Fuzzy System for Detection Fuel Consumption of Helicopters Turboshaft Engines. One of the urgent problems of helicopter flight operation in the choice of optimal flight modes in terms of fuel efficiency. The most rational in this case in the use of the theoretical methods, in particular the methods of numerical modeling and intelligent information technologies. To implement this approach, it is necessary to have a mathematical model of the helicopter dynamics, which includes, among other things, a module for determining fuel consumption. One of the promising directions for the development of helicopter operation control tools in the use of artificial intelligence components in their composition, production rules, fuzzy logic, artificial neural networks, hybrid neuro-fuzzy architectures, genetic algorithm, etc. Therefore, the task solved in this work is relevant. Currently, there is a lot of research in the field of monitoring helicopter turboshaft engines, including using artificial intelligence tools. Therefore, the task posed in the work is relevant. The mathematical model for determining the specific fuel consumption of helicopters' turboshaft engines on the example of the TV3117 engine, which is part of the power plant of the Mi-8 MTV helicopter, is described by this author's group. The specific fuel consumption of helicopters' turboshaft engines depends on the air consumption in the combustion chamber, the specific engine power, and the ratio of fuel and air consumption of the combustion chamber. This parameter directly depends on the type of aviation fuel. Calculation of the thermogas dynamic parameters of helicopters' turboshaft engines, air consumption in the combustion chamber, specific engine power, ratio of fuel and air consumption in the combustion chamber, is calculated using a helicopter's turboshaft engine's neural network model developed by this team of authors in this slide. Currently, the hybridization of neural network with fuzzy logic can significantly increase the efficiency of automatic control system with Neuro-Fuzzy network due to the fact the disadvantages inherent of one of the technologies are compensated by the advantages of the other. According to the above, the implementation of the developed system was carried out on the basis of ENFIS and adaptive Neuro-Fuzzy system that implements the Sugeno-Fuzzy inference system in the form of a 5-layer neural network of direct signal propagation. The first layer of which contains in the term of the input variables the current values of the helicopter's turboshaft engine thermogas dynamic parameters and their delayed values. In the process of model formation, the sample of initial data was divided into two parts: training and testing. The input parameters of helicopter's turboshaft engine mathematical model are the values of atmospheric parameters: flight altitude, temperature, pressure, air density. The parameters recorded on board of the helicopters: gas generator rotor RPM, free turbine rotor speed, gas temperature in front of the compressor turbine, reduced to absolute values according to the theory of gas dynamic similarity. Detailed analysis and preprocessing of input data is described in detail in the other works by this author's group. A fragment of expert knowledge matrix for intelligent control of helicopters' turboshaft engine specific fuel consumption is given in this slide, this table. Diagrams of the results of training a Neuro-Fuzzy network by the backpropagation algorithm and by the hybrid methods are presented in this slide. From this figure, it follows the hybrid methods train the network is a number of epoch 105 times less than the error backpropagation algorithm. Therefore, a hybrid method was used to train the neural network in the work. When developing a Neuro-Fuzzy network, the choice of membership function is extremely important. This table shows the network training error obtained for various membership functions as a result of network training by the hybrid method. The results of tuning the membership function in the case of 2 and 3 terms of input variables is shown in this slide. In the course of research, it was found that the two slides Gaussian membership function provided the smallest error. The type of fuzzy inference surface for different types of membership functions also presented in this slide. In order to implement the above proposed method, a universal program was created for generation according to the given values of the knowledge base matrix for the fuzzy controller. This program works as follows. Saved matrix of elements is called. Largest modular values of each of input and output are determined. Range of values of each input and output is divided into terms with a step specified by the user. According to the affiliation of the variable values from the resulting matrix, at each step, input-output rules are formed in one or another terms. Rules and combined of the output does not change its values when the inputs change. Same rules are also combined. After executing this method, a rule base is formed. The results of assessing the influence of the number of membership functions on the performance indicators of the task being solved are given in the left top table. The research of the influence of the number of device inputs of identification efficiency indicators shows in the left bottom table that the best results are achieved with 2-3 device inputs. The combining diagrams of the initial data and the results of controlling the specific fuel consumption as well as control error are shown in this figure. Also, using the Neuro-Fuzzy system developed above data on specific fuel consumption in various operating modes of the TV3117 engine obtained. The initial data for the calculation were taken from research by Professor Rodriguez Salas and him group, where the engine's nameplate data is also presented, with which the calculation results were compared. The calculation results and passport data are summarized and presented in figure. Curve 1 calculated data, curve 2 passport data, curve 3 calculated data obtained by Vadim Yefimov. As a part of the experiment, the ENFI's Neuro-Fuzzy control algorithm was compared in accuracy with other machine learning methods, random forest, extra tree, and multilayer perceptron classifier. Left table. The ENFI's Neuro-Fuzzy control system as a whole showed good generalization ability with respect to LP. However, the extra tree algorithm in turn showed an advantage according to the F1 measure, since it is an ensemble method. The results of determine errors of the first and second kind in terms of fuel consumption of helicopter's turboshaft engine are presented in right table. Comparative analysis of the obtained results confirmed that developed helicopter's Turboshaft engine fuel consumption control Neuro-Fuzzy methods provide the minimum error in the solving task in the process of helicopter flight operation. The conclusions are presented in this slide. Thanks for attention.